Hello everyone, let's talk about rotations today. It's another type of transformation where we change an object. And so we'll go ahead and jump right in here. A rotation is a transformation in which a figure is turned about a fixed point called the center of rotation. So we'll get to this next part here in a moment. Take a look at this little diagram here on the right hand side. This is figure R. It got overlapped a bit by the text, and it's this flag-shaped figure. Now, depending on the point of rotation, we would end up with an image in a different place. Let me use tracing paper to outline this flag. This is our original pre-image before the change. Now, let's imagine for a moment that your point of rotation was here. This is your center of rotation. Then when you rotate the image, you can see how the flag moves. All right. Let's imagine for a moment that the center of rotation was here. Well, then that's how the flag moves. Let's imagine that the center of rotation is here, and that's how the flag moves. All of those are different than how the diagram is actually created. They happen to put the center of rotation down here. Well, that's then how the flag moves when you rotate it about that center of rotation. So the center of rotation doesn't have to be on the object itself. It could be off the object, and that's what you're seeing here. They put the center of rotation down here. They're calling it a point P. So this line is really just a construction line. They're just drawing a straight line from the center of rotation to a particular point on the object itself, and then when we have this rotation, here's your image. This is now R prime. Again, they're just drawing a construction line from this center of rotation to the same corresponding point. And they're saying, hey, that's how many degrees of rotation we end up with. Rotations are very complicated in theory, so we're limiting it to just a few rotations. We are only going to rotate 90 degrees, 180, and 270, and we have specific rules to follow to make that happen. If we were to do any other rotation, it would be too complicated and beyond what we want to handle now. All right. Like I said, I'm going to come back to filling in this blank a little later on. It's a little bit obscure without an example to go with it, so we'll come back to that. The only thing that I want to point out here, first of all, is that when we rotate, we are always going to rotate counterclockwise. Always. So there's a difference between clockwise and counterclockwise. And the reason for that is if you think of your XY coordinate grid and we number off the quadrants, we number them off in an order of a counterclockwise rotation around the origin. So quadrant 1, and then counterclockwise from that, we either get to quadrant 2, and then quadrant 3, and then quadrant 4. So the way that we name the quadrants is in a counterclockwise direction. So we'll just stay the same and rotate our objects in a counterclockwise direction. That's the first point. The second point is our center of rotation is always going to be the origin. There's a few instances where we're going to take it away from the origin, and I'll show you when that happens. But for these rules to work, if we're going to use these rules, it must rotate around the origin on our grid. And so, again, instead of just using an X and a Y to represent the ordered pair, we're using A and a B, but it's the same idea. This is what we have to do. If we are rotating 90 degrees, we're going to take our ordered pair and make two changes. First, this rule will tell us that we're going to switch the order around, so what used to be in back is now in front. And then secondly, you must change the sign on whatever number is here in front. Remember, this does not mean make it negative, this means make it the opposite of that number. So if it starts positive, it becomes negative. If it starts negative, it becomes positive. That sign means the opposite of that number. For a 180 degree rotation, the numbers stay in the same spot. What's in front stays in front, but now we change the sign on both. For a 270 degree rotation, we switch the pair around, so what used to be in back is now in front. And then we change the sign of the number in back. So this is what I was trying to bring to your attention here. What's in bold. It's important enough. I want you to bubble it in so that you can see what we're talking about with the use of this negative sign that's in front of the number. So this symbol, this notation of negative b means the opposite of b. Therefore, if b were positive, it would become negative. And if b were negative, it would become positive. So this notation communicates to us when we see it, it's the opposite of that original number. So let's take a look at an example. Oh, I guess I should say first let's fill in the blanks here for the directions that we'll use when graphing. This is similar to what we've seen before the past couple of days of notes. First, we're going to graph the pre-image and label its vertices. Next, we'll use the coordinate rules provided to us to find the coordinates of the image. And then once we have those coordinates, now we're ready to graph the image. And don't forget to label the vertices and be sure to use prime notation. So here's example 1, part A. We have this quadrilateral, KLMN. It has these vertices, and it's already been plotted for us. So that's your pre-image. That's the first step already taken care of. It's a little bit off. We really did want L to be right there, and we really did want M to be right there. So it's just a little bit off. So there we go. There's my quadrilateral. We're going to rotate this 90 degrees about the origin. So I take a look at my rule, and the rule says for 90 degrees, switch the numbers around, so what used to be in back is now in front, and then change the sign of the number in front. So I always do it in that specific sequence. Watch how I do this. So you can see we have each of these set up. So first of all, there's my K prime with the empty parentheses. There's my L prime. We're just setting up the information here. There's my M prime with the parentheses. There's the N prime with the parentheses. Okay, so to follow the rule, first switch the numbers around. So I'm going to go through all these and switch the numbers around. So 3, 2 is now 2, 3. On point L, which is 4, 2, that now becomes 2, 4. Point M, which is at 4, -3, is now -3, 4. Point N, which is 2, -1, is now -1, 2. We're not done, that's just the first part. Because with the rule, the first thing you have to do is you have to switch the numbers around. Then you go in and you change the sign on the number in front. So I just do all of those changes at the same time with all of those numbers. So here with K prime, we change the sign in front, so now that's a -2. With L prime, we change the sign in front, so now that's a -2. With M prime, we change the sign in front, so now this is a +3. And for N prime, we change the sign in front, so now this is a +1. So it helps if you use a second color in these cases, so you can keep track of which signs you changed and which you haven't. Let's plot these points. So K prime is at -2, 3. So from the origin 2 to the left and 3 up. Yes, K prime, there it is. L prime is at -2, 4. L prime. M prime is at +3, 4. So 3 to the right and then 4 up. And lastly, N prime, 1 to the right and 2 up. And then connect those. Now there's a few things to say here before we jump on to the next example. One, again, it is helpful if you have tracing paper, you can kind of see where this is going. So I'm outlining the original pre-image, and I have to also draw that X and Y axis, because when we rotate this thing, we put our pencil down here at the origin, and then spin the paper, and a 90-degree turn is like a quarter turn. And so when I do this, it's a good way just to check to see if my final sketch is correct. Yes, the diagram is in fact where we graphed it, so we know we're good. And so that's one technique you can use. I know you may not have tracing paper around, but that's an aid to help out if you like. So we rotated in that counterclockwise direction by using those rules, and we rotated around the origin. That was our center of dilation. Let's now take the same pre-image. Again, point L and point M really are right there on the grid. There's that side. This time let's rotate it 270 degrees. I'm going to set up my field here, so there's the space for K prime with its parentheses, L prime, M prime, and N prime. Okay. Well, let's check out what that rule is for a 270 degree rotation. It says switch the numbers around, so it used to be in back is now in front, and then we'll change the sign on the number in back. Alright, so first I switch all the numbers around, and so K, which is at 3, 2, is now 2, 3. L, which is at 4, 2, is now 2, 4. M, which is at 4, -3, is now -3, 4. And then 2, -1 for point N is now -1, 2. So we switched all the numbers around. Then we go back in and we change the sign of the number in back. So on K prime, the y coordinate is 3, now it's -3. On L prime, the y coordinate is 4, now it's a -4. On M prime, the y coordinate is 4, now it's a -4. And lastly, for N prime, the y coordinate is 2, it's now -2. And then we'll plot those points. Okay, so K prime is at 2, -3. So 2 to the right and 3 down. L prime is at 2, -4. So 1, 2, 1, 2, 3, 4. M prime is at -3, -4. So 1, 2, 3 to the left, 1, 2, 3, 4 down. And lastly, N prime is at -1, -2. So again, I can use my tracing paper here to double check. So here is my pre-image, and to do a 270 degree rotation, that's 3 quarter turns. That's 3 turns of 90 degrees apiece. So here's a 90 degree turn, that's what we saw in example A. Here's another 90 degree turn, which means we've gone up to 180 degrees of rotation. And then here's my third 90 degree turn, and that adds up to 270, and that's correct. Okay, there's one last detail that we want to talk about. So I'm going to take another color here, and I'm drawing some construction lines. These are not part of the actual graph, but let's pick a pair of corresponding points. For example, let's pick the K's, K and K prime. If I were to draw a construction line from the center of rotation to point K, and then I drew another one from that center of rotation to K prime, what you should see here is a pair of lines that, if you were to rotate one to the other, matches that 270 degree rotation. Let me also do that on part A. Let's pick a pair of points. It, again, doesn't have to be the K's. Let's use the L's. All right, so I'm going to draw a construction line from the center of rotation to point L, and then to point L prime. And so if you take a look at that, that should look like a 90 degree rotation. They look to be perpendicular lines, and they are. So that's a quick way that you can actually check to see, without tracing paper, if you have placed the points in the right spot. You could do this with M and M prime, draw a pair of construction lines. You could do this with K and K prime. You can do this with N and N prime. It'll work for each of those if you have in fact drawn it correctly. So let's pretend that you have a point that is in the wrong spot. Let's say, for example, that you accidentally made a mistake and point M prime got put in the wrong spot. Let's say M prime is somewhere way out here. Well, if you draw construction lines to the original point M and then to this imaginary M prime that's in the wrong spot, and you check to see if you have perpendicular lines, you'll see that that doesn't work. It's not in the right spot. So go back up to the top. That's what these blanks were talking about. In a rotation, these rays, these are the construction lines that we were just talking about here, when you can test to see if your points are in the right spot. These construction lines, you could think of them as rays, drawn from the center of rotation to a pre-image, as well as its image. So that's what we were doing with the pair of matching points, K and K prime, or L and L prime. Form the angle of rotation. So even the construction lines will match the angle of rotation. All right. If they don't match the angle of rotation, that means our point is in the wrong location. We made a mistake. So it's a way to check your work. We'll see that again in our next example when we do a 180-degree rotation. All right, so next page over. Here it says you try, but we'll go ahead and just work this through together as it's a 180-degree rotation. Here we need to first of all graph the pre-image. So point A is at -2, 4. Point B is at -4, -1. Point C is at -3, -3. And point D is at -1, 0, so left 1 but neither up nor down. So here's my quadrilateral. Now because when we're applying the rule we have to like move the numbers around, it's helpful to create a table, and so here you have it in a row, points A, B, C, and D. So I would create now another row of A prime, B prime, C prime, and I didn't space that out right to give myself D prime on the same row, so I'll just jump down to the next row. There's D prime. Okay, that's just kind of setting up our space so that we can now apply the rule. What is the rule? Well, we have to go back and take a look at that. For a 180-degree rotation, it says keep the numbers in the same spot. We're just changing the sign on both numbers. All right, well, that's pretty easy. So A, which is at -2, 4, and B, which is at -4, -1, and C, which is at -3, -3, and D, which is at -1, 0, all of those numbers have to change the sign. So I come back in my second color and I change all the signs. -2 becomes +2, and +4 becomes -4. -4 becomes +4, and -1 becomes +1. Here for point C prime, -3 becomes +3, and again, same for the y-coordinate. D prime, -1 becomes +1, and 0 stays 0, because that's neither positive nor negative. Let's plot these points. Alright, so A prime is located at +2, -4. So 2 to the right and 4 down. Here's my A prime. B prime is at 4, 1. So 1, 2, 3, 4 to the right, 1 up. C prime is at 3, 3. And D prime is at +1, 0. So there's my D prime. So let's use that technique we saw earlier where we draw these rays, these construction lines, to these matching points. So we could pick the A's, we could pick the B's, we could pick the C's, the D's. It doesn't really matter. Let's just pick the A's. So if I were to draw a construction line from that center of rotation to point A, and from that center of rotation to its corresponding point at A prime, and then you take a look at how those construction lines rotate, it should match the rotation we did of the figure itself. So again, that's a way to check your work. You do that with each of the points. If you did that with the B's, and you did that with the C's, and you did that with the D's, you can see that each pair of those corresponding points does fall on that straight line, which is a 180-degree rotation. So for those first three examples, we followed the rule where we were rotating our object on the coordinate plane. And then all of a sudden we take the coordinate plane away. Take a look at example 2 and 3. When we have examples like this, I find that a lot of my students have trouble with these because they look different. They're saying, wait, what is the rule that I'm supposed to use? Well, hold on, this is a very different objective here. We're not plotting the image because it's already given to us. It says the quadrilateral is rotated about point P. Find the value of x and y. X and y are on the side lengths of the figure. So we're not using the rule here. That's a completely different type of question. So in example 1 and then the you try above, that was about using the rule to find the image. This is a different emphasis. Here's the quadrilateral they're talking about. That's the four-sided figure. We then rotated it certain degrees. You'll notice it doesn't match any of the rules we used. That's okay because we're not using the rules. And the dashed line is where it is ended up. So think of this as the image. So then what are these other little lines? Those are the construction lines. Remember, we were talking about you can draw construction lines to a pair of corresponding points, and that will give you the angle of rotation. That's what they're doing here. They're saying this is my point of rotation, my center of rotation. Here, let's draw a construction line to this little bottom point on that quadrilateral. Let's draw another construction line to its corresponding point here on the image, and the rotation between those two construction lines tells us what that angle of rotation is. But we really don't need that information. What we're just trying to do is solve for x and y. X is on a side length. It's not on an angle of rotation. So we don't even need this 110 degrees. We just don't need that number. We need to figure out x and y. So some of the side lengths are given to us, like this is a 4 and this is a 6. Some are not. Now we can do this without tracing paper, but as a way to explain it, I'm going to set it up using tracing paper, so hopefully it makes a bit more sense on what we're talking about. So here is the outline of the pre-image. There's the center rotation. And take a look at this side length, which is told to us as being a length of 4. Okay? So when we rotate this object to its new location, we're trying to determine where does that 4 end up. Those are the corresponding sides. You can see the 4 is over here, so I'm going to label that on my diagram. That's the side of length 4. Let's go back and take a look at the 6. So again, on my pre-image, this is a side of length 6. Where does that 6 end up when we rotate the object? So we rotate the figure, and that 6 ends up over here. That's the corresponding side. So I'm going to label that as well. And hey, look, that's already given as a 3x. So what we're saying is that these two sides are corresponding sides. Not only are they corresponding, but they are equal. Because you observe that when we did the rotations, the figure was a rigid transformation. It stayed the same size and shape. That meant that the length of this segment in the previous example, this length from A to B, is equal in size to this length of A prime, B prime. It doesn't get bigger or smaller. That's the same concept here. This length of 6 is still a length of 6. It doesn't get bigger or smaller. A rotation is a rigid transformation. That means that this information here can help us solve for x. Because if this length is 6 and this length is the same size, which is also 6, then we can set this 3x equal to 6 because they are equal in size to each other. And that's how we solve for x. We get a result of 2. Alright, so now we want to find out this value of y. So again, I'm taking a look at my original pre-image. Here is a side labeled as 7y. I'm going to figure out where does that side end up when we rotate the figure. So we rotate that figure, and that side ends up here, right there. This is the 7y. So those two sides are equal in length. So the 7y equals the 3x plus 1. Well, we have two variables which would normally give us trouble, except we already solved for x, and so now we can plug that value in. So it looks like 7y equals 3 times the value of 2 plus 1. So that means we have a result of 1 for y. So I was using tracing paper to show how the figure rotates to find the matching sides. Your goal is to be able to do this without tracing paper, just to kind of look at the figure and determine what those corresponding sides are. So take a look at example 3. Let's see if we can do this without that tracing paper to help us out. So here, this is the direction of rotation. We don't really need to know that it's 80 degrees. That doesn't really matter here. The idea is we're going to look at this triangle and figure out how each of these sides line up to the triangle sides in its image. So I'm going to take a look at this 15, as it's labeled as 15. I'm thinking, okay, this 15 is coming in and touching this construction line. It doesn't make the straight side. It's sort of like this bent side. So I want to find this matching pattern on my image. So I want to find a side of a triangle that's close to the center of rotation, not far away from it, but close to the center of rotation. And that looks to be this side right here. Can you see how the 15 and this side labeled as 3a are the corresponding sides? They are both sides that are the closest to that point of rotation. So that means we would set 3a equal to 15. So there's one of them. So now I'm taking a look at this side described as 4b, and I'm thinking, okay, where does that land? This side described as 4b is a side that is farthest away from that point of rotation. So on the image, I want to find the side that is also farthest away from that point of rotation, and that's the 2a plus 6. So those would get paired up. The 4b is equal in length to the side labeled as 2a plus 6. Well, again, we have two variables, but we already solved for a, so we're going to take that value of a and drop it in. So we have 4 times b equals 2 times the value of 5 plus 6. So 4 times b equals 16. So b is 4. So I want you to try one. You can see here right below that we have a you try problem. Again, it's the same idea. We are taking a quadrilateral, we are rotating it to end up in this new place. So there's the image, you can see the direction of the rotation. We're trying to solve for x and y. So once again, turn off the video, see if you can work it out. Turn on the video when you are ready to check your answer. I'm taking a look at my pre-image, and here's the side that is closest to the center of rotation. So on the image, here is the matching side that is closest to the point of rotation. So those two sides go together, the 4y and the 3x minus 5. But I have two variables, I can't solve for it yet. So we'll come back to that in a moment. Let's find another pair of sides. I just want to point out, for example, that this side of 6 that you see here on the image, that's the side that's farthest away from the point of rotation. So on the image, the side that is farthest away from the point of rotation is here. So that's also 6. And the value of y, or x, is not labeled here. So that's kind of a decoy. We don't really use the 6. It doesn't help us out any. So let's take a look at the 8. So the 8 then is the side that's sort of connecting this closest and furthest side. So that would pair up with the 2y, which again is connecting the furthest and closest side. So the 8 and the 2y are paired up. So what that means is we have two equations. We're going to start by solving for y first, and then we'll take that information, plug it into the previous equation, so that we can solve for x. And we end up with a result of 7 for x and 4 for y. This last you try, this is back to what we had started with, where we were using specific rules on the coordinate grid. So again, you try this one. Here we have a trapezoid PQRS. Plot the pre-image, apply the rule for 270-degree rotation, and then plot the image and check your results. So turn off the video and do this problem. Turn it back on when you're ready to check your answer. First, I'm going to make a table. Here's point P, Q, which is at 4, 4, R, which is at 4, -1, and S, which is at 2, -2. And this is really just so I can get my new values ready for point P prime, Q prime, R prime, and S prime. Plotting the pre-image, point P is at 2, 5. Q is at 4, 4. R is at 4, -1, and S is at 2, -2. Alright, there's my trapezoid. We're going to apply the rule which says first, switch the numbers around, and then change the sign in back. So the y coordinates change their sign. And that's what we'll plot. So P prime is at 5, -2. Q prime is at 4, -4. R prime is at -1, -4. And lastly, S prime, -2, -2. So again, you can check your work by picking a pair of points, drawing construction lines to each of them. So let's pick point R and R prime as an example. If I were to draw a construction line from the origin to point R, and then from the origin, that's point P. Well, that's not good, so that's point P. This is point R. I knew something was off. Let's scratch that one out. If I draw a construction line to point R, there, that's what we want to look at, and then R prime, what you should see here is that we have perpendicular lines, and that's exactly right. That's our 270-degree rotation, which means on the inside here that's 90 degrees. And there we go.